All right, so in this video, we're going to talk about hybridization. This comes up a lot in organic chemistry, and we touch on it a little bit in Gen Chem. I'd like to sort of go over sort of the highlights that will behoove us to pay attention for Chem 42. In hybridization, we're basically talking about the mixing of atomic orbitals to make hybrid orbitals. So let me just write that down. So we're going to be talking about mixing. I'm going to abbreviate atomic orbitals as AO, right? So we're going to mix some atomic orbitals that are of comparable energy, right? Mixing atomic orbitals of similar energy. I'm going to say energies and shapes. To make hybrid orbitals. And I'm going to abbreviate those HO. Of slightly different energy and shape. And I'll draw what that is when we get to it. And this right here is what we're going to be used to pair electrons in valence bond theory. So if you remember, so this will be used to pair electrons in valence bond theory. So I'm going to abbreviate that VBT. So if you remember, from Gen Chem, when you're talking about valence bond theory, there's a couple of different ways that we can make a molecular orbital, right? We can talk about taking a half-filled orbital and allowing it to overlap with another half-filled orbital, and together they're going to create a molecular orbital that's lower in energy, so heat is given off, right? When you make a bond, all bond making processes are exothermic, that kind of thing. So maybe this is, slowly coming back for some of you. There's another option where you can have an empty orbital and a completely filled orbital, right? So for like the coordination complexes, and we talk about, we can have a filled orbital where we get two electrons paired up, and an empty orbital, those can share. We're going to talk about the situation where you have two atomic orbitals, each with one unpaired electron, and those are going to overlap, and we're going to form a molecular orbital. So let's just sort of like remind ourselves what we're dealing with here. In this particular class, we're going to be focused on carbon mostly. Sometimes we'll talk about nitrogen, occasionally oxygen, but mostly carbon, right? It's an organic chemistry class. So we're going to be dealing with the 2s orbital and the 3 different orientations of the 2p orbitals. So if we have an s orbital, we remember it's kind of spherical, right? And we're going to combine this with a p orbital. I'm going to draw just one. We have 3 different orientations, right, for the p orbitals. But we get a situation like this. So for our p. And what you're going to get for this hybrid is you're going to get a very large lobe. And that's going to be used to overlap. That's where we're going to say, hey, this is where the electron is probably spending most of its time, right? That's going to overlap. And then we get this little like nugget on the end. So this hybrid is pretty useful in explaining bonding and molecular geometry, right? The larger lobe gives us better orbital overlap. So let me write that down. Our larger lobe, put that here. This is going to afford better orbital overlap. And so therefore, we'll have a stronger bond. So there's a few things about hybridization, and I've noticed just sort of like over a few semesters, students mentioning in Gen Chem anyways, things like, what's the point? Like, why am I learning this? Like, what's going on? When you get to organic chemistry, which here you are, right? We're talking about hybridization in terms of basically the molecular geometry, so the shape of something. When we go to attack something and I tell you this is sp2 hybridized, what I'd like for you to do is to say that thing's flat, like a pancake. I can come in on the top, I can come in from the bottom, right? If it's sp3 hybridized, I want you to imagine that it's not flat, right? And it's kind of like a little shrub and there's some stuff in the way. How big is the stuff in the way? So when we're talking about hybridization, really what we're trying to do is just wrap our minds around, like, what does this thing look like when we're trying to attack this site and form a new bond, you know? So with hybridization, there are some things to focus on. And one of them is that our atomic orbitals, so our atomic orbitals are going to come in with similar energy. And remember, so like the p orbitals and the s orbitals, right? We have that sub-level splitting. They don't have the same potential energy. If you remember from Gen Chem, they're similar. They're not too far off, but they are different, right? They're not the same. These are going to undergo hybridization. So atomic orbitals of similar energy undergo hybridization. And they're going to form hybrid orbitals like we see above. Our s orbital and our p orbital are going to combine, and we're going to make that hybrid. The number, so if you remember from molecular orbital theory, this is a similar concept. The number of hybrid orbitals formed is going to equal the number of atomic orbitals that we mix. And as we go through and talk about the three different types, because we'll focus on three different types in this class, I will point out these are the atomic orbitals we're going to mix. And so therefore, for example, if you take the s orbital in all three different orientations of the p orbitals, right? So you have three p orbitals and an s orbital, that's 4 atomic orbitals. If I mix all those together, I should get 4 hybrid orbitals, right? If I take the s orbital and only 2 of the p orbitals, I can expect 3 hybrid orbitals to form. So it's kind of just like with molecular orbital theory when you're doing the, you're making your molecular orbitals and you're doing a linear combination of atomic orbitals, you're going to get the same number of hybrid orbitals, or in other words, molecular orbitals, right, that are formed. So that's sort of, if you're remembering MO theory at all, it's similar. So it is not required that all of the half-filled atomic orbitals actually participate in the hybridization. So you don't have to have all of these actually participating, and we'll talk about where we see that occurring when we get to it. So it is not required that all of the half-filled atomic orbitals, participate in the hybridization. So it is not required that all of the half-filled atomic orbitals participate in the hybridization. So it is not required that all of the half-filled atomic orbitals participate in the hybridization. So it is not required that all of the half-filled atomic orbitals participate in hybridization? And another feature is that we can have completely filled atomic orbitals that are of similar potential energy participating in the hybridization. So you can have a completely filled atomic orbital. So in other words, you have an atomic orbital that has two electrons that are paired, they're spin paired, right? One up, one down. Those, of similar energy, those can participate in the hybridization. So you can have completely filled atomic orbitals of similar energy participating in hybridization. Another feature that we notice is that, in other words, this is basically just another model. So hybridization is a concept and only occurs during bonding. So in other words, this is not something somebody's like spying on, right? We're not seeing this happening. This is a concept. It's another model. It's where Lewis falls flat and we have to come up with another sort of, I don't know, illustration, right? To sort of explain a molecule that we have data to support its existence, like methane, for example. So hybridization is a concept. I'm going to underline that because this is not something that somebody has like pinned down, you know. Nobody is saying, hey, I have a crystal structure here of a hybrid orbital. This is just, it's a concept, it's a model, it's a cartoon illustration of how we might rationalize bonding and molecular geometry, right? So this is a concept and only occurs during bonding, not in isolated atoms in the gas phase, which is basically where we study almost everything else, right? So we don't notice this hybridization as occurring in an isolated atom in the gas phase. A carbon atom, right, isolated, just hanging out by itself in the gas phase, has not been seen or found to undergo this hybridization. This is kind of like electronegativity, right? This is something that you notice when your atoms are involved in bonding with other atoms. This is something that occurs or that we believe could occur, or it's a model, in other words, or a concept, right? An illustration that helps to explain bonding. So this can't be just a single carbon atom out in the wild hanging out by itself. This is like, hey, you're in methane and I'm noticing that you have 4 bonds and these are the bond angles. I have an X-ray crystal structure of this molecule. Like, how do I explain this, right? That kind of a thing. So the next thing that we can sort of write down about this is that hybridization can allow us to predict molecular geometry, which is pretty handy. So hybridization can allow us to predict molecular geometry, or in other words, the shape of a molecule. And you might be like, well, who cares, right? Because that's what I thought too. But when we go to do synthesis, you want to know where these electrons are hanging out. Chemistry is all about the exchanging or, transfer, sharing, whatever of electrons. So you want to know where these orbitals are hanging out, right? What's the geometry of this particular species? Because I need to imagine that these atomic orbitals, or at least these, maybe the lone pair, is going to participate in some sort of chemical reaction. If it's tied up geometrically and sort of like out of commission, then just because they're there doesn't mean they're available. You know what I'm saying? It's kind of like if you've got like money tied up in stocks. It's not liquid. It's not available. You can't go into the store and use your money that's in stocks to buy something, right? So it's how I sort of view this. So hybridization sort of allows us to predict molecular geometry, giving us an idea about, hey, this is like kind of what's going on with these electrons. Just because there's a lone pair of electrons on that nitrogen in that particular molecule doesn't mean that they are readily available to attack something else and form a new bond. So this is handy for us in organic chemistry with our syntheses, right? So and the last thing I want to mention is that the larger, so look at these things, right? This hybrid orbital, that lobe up there, this, so we're talking like that big fat lobe right there is going to overlap. It's longer, it's bigger, right? The orbital overlap is better. So the larger lobes of the hybrid orbital are what overlap to make the new bonds. So to form the new molecular orbital. And you remember from Gen Chem, the better the overlap, the stronger the bond. So you got these larger lobes of the hybrid orbital, a better orbital overlap, you're going to get a stronger bond. And that's going to come up again and again when we go through these examples. So let's move into what we care about in organic chemistry. When we were talking about Lewis theory, we discussed how to draw these different molecules. So I'm going to go back to methane. So CH4, right? We have data, extensive data, to suggest that this particular molecule exists. What do we know about this? We know that the 4 valence electrons on carbon, 4 valence electrons on carbon are going to occupy the 2s and 2 of the, 3 2p orbitals, right? There's 3 different orientations for these 2p orbitals, right? We've got 2px, 2py, 2pz. There's only 4 valence electrons on carbon. It's in group 4. 2 of them are going to be paired up in the 2s orbitals, and then 2 of them are going to be hanging out in the 2p orbitals, right? But there's 3 2p orbitals. And so according to Hund's rule, we're going to fill each orbital with an electron unpaired, right? Before we cut, everybody gets one helping before we come back and spin pair them, right? So these are going to be hanging out in those 2p atomic orbitals, but the electrons in the 2s are paired up. So I'm going to draw an energy level diagram just for the valence electrons so you can see what I'm talking about. We're going to be pairing up the 2s electrons. We're going to have 2 unpaired electrons, each in the 2p orbitals. When you look at this, so we got for carbon, in methane, we got 1 times a single carbon. I'm going to circle that. We have increasing energy in this direction. We're going to imagine we have our 2s orbital, and I'm going to exaggerate the difference in energy. These are pretty close to each other, right, in potential energy. But just to give us some space to draw this out and imagine what's going on. So for carbon, we're just doing the valence electrons. We've got 2s2, 2p2, right? Two of those electrons are paired up in the 2s orbital, and then two of them are unpaired. When we're dealing with valence bond theory, we're going to be imagining here that we get two electrons, right, that are unpaired. So we have two half-filled atomic orbitals, those 2p orbitals. Those are going to be overlapping, right, with a half-filled atomic orbital on a hydrogen. You're dealing with CH4, however. So if you're looking at this, you'd be like, all right, it seems like, according to valence bond theory, I should be able to make, so let me just write this out, we should be able to make two single bonds at a 90 degree angle, and you imagine the carbon should have a lone pair of electrons, right? The lone pair of electrons are the two paired up electrons in the 2s orbital, aren't they? So if we're talking about, hey, you got two options here. We're going to take a half-filled orbital and allow it to overlap with another half-filled orbital from some other atom. That's fine. We have two half-filled orbitals here. Or you could say, well, I'm going to take a completely filled orbital and allow it to overlap with an empty orbital on another atom. Well, here's the thing. Hydrogen, we take our 4 for methane, 4 hydrogen. Each one of those has a half-filled orbital. There's no empty orbital. We have a 1s orbital, and each one is half-filled. So now what are you going to do, right? Seems like you should only be able to bond with 2 of the hydrogens, and then the carbon should hang on to a lone pair, doesn't it? But we have evidence to, suggest that methane exists. So this is a molecule that's, nobody's arguing the existence of methane, right? And by the way, we have an X-ray crystal structure of this particular molecule suggesting that the bonds are not 90 degrees. They're a little closer to, say, 109.5. So what the heck is going on, right? If we say, what if we mix the 2s and the 2p orbitals? So I'm going to take these, mix them together. And what do I have here? I have a 2s orbital, and then I have 3 different orientations of the 2p orbitals. 1, 2, 3. I've mixed 4 atomic orbitals together. I have now created 4 sp3 hybrid orbitals. I'm abbreviating that HO. So I've got 4 sp3. What does sp3 mean? We have an s orbital in all 3 of the p orbitals. Then you're going to take those 4 valence electrons and you're going to sort of like re-deal them like cards, right? According to Hund's rule, everybody gets 1 electron before we spin pair anybody. So now check it out. We've got 4 hybrid orbitals. Each one is half filled. Now it seems like, yeah, we could probably allow each one of those hybrid orbitals to overlap with a half-filled orbital on hydrogen and make 4 single bonds. Each of these can form what we call a sigma bond. Put a little star here that says all single bonds. This is going to be worth remembering. All single bonds are sigma bonds. So when we draw out the molecule for methane, what do we have? I'm going to put the carbon in the middle so that it's easy to spot. Put the little C there. I'm going to take each one of those hybrid orbitals. So remember, this right here, a little arrow over here, I've got 4 times my sp3 hybrid orbitals. I've made 4 of these. And each one has an unpaired electron, and then this little nub. So this is my sp3 hybrid orbital, right? I've got one here. When we draw these out, we don't often draw the little nub in there. So there's the lobe, right? That's going to overlap with the half-filled orbital on each one of the hydrogens. And I have formed 4 sigma bonds. So that's carbon. I'll put the little H here so that we can see what's going on. And we'll color this in. Those are going to be my sigma bonds. Those are my single bonds. So here we have 4 electron groups on my central atom. So my carbon has 4 electron groups. Remember, these groups can be bonding or non-bonding. So in other words, my hybrid orbitals can form sigma bonds, right? And they can also hang on to lone pairs. When we get further into the semester and start talking about amines, especially aromatic amines, we'll be dealing with the hybridization of a nitrogen, and it'll be important for us to note that these lone pairs of electrons, right, are hanging out sometimes in these hybrid orbitals, and the geometry, the electron geometry, is going to be important, because you might think those are available to be using to attack something, like deprotonating something or forming a bond with something or whatever, and sometimes they're not, right? They're tied up in a pi cloud. When we get through to that section, I would like you to lean back on this hybridization video and sort of remember, like, hey, geometrically speaking, that is just not possible. These cannot overlap. They're tied up in this pi system, right? So we got 4 electron groups on the carbon. They can be bonding or non-bonding. In this particular case, they are all in bonding orbitals, right? Theta, so that's going to be our bond angle. That's this here. So here's theta, is going to be about 109.5 degrees. Remember, we have this general category for anything that has 4 electron groups, right? Bonding or non-bonding. It falls into that approximately 109.5 degree category. The electron geometry is what we call tetrahedral. Right? So it's not flat. That's going to be important for us to remember as we move through this particular course. All right. Here we have a molecule where we're dealing with all single bonds, basically, right? We have CH4, everything is singly bonded. All single bonds are sigma bonds. That's important to remember. So I'll highlight this. These are all sigma bonds. We have a situation where some molecules have double bonds. What the heck are those? Well, it's not simply 2 sigma bonds, right? So what about double bonds? Or I guess you could say, what about when you have a central atom like carbon, since it's organic chemistry here, where you don't have 4 electron groups? What if you only had 3, right? So what about double bonds? What the heck are those in the first place? So a double bond is not 2 single bonds. It is not simply just two sigma bonds, right? All single bonds are sigma bonds. A double bond is not therefore two sigma bonds. So therefore, a double bond is not two sigma bonds. What is the take-home message here is basically these double bonds, right? When you have one, they're not made up entirely of hybrid orbitals. All of these hybrid orbitals can make sigma bonds, or they can hang on to lone pairs of electrons. In order to make a double bond is one sigma bond plus one pi bond. And you can't make this with a hybrid orbital. You can, however, make it with an unhybridized p orbital. So you got to leave one of those p orbitals out of the mix when you're doing the hybridization. So let's talk a little bit what this might look like. Let's take something we're all pretty familiar with, I guess back with algebra maybe, and draw out our little Cartesian coordinate system. We'll keep it simple. We'll call this the y-axis. That was a terrible straight line. We'll try to call that the x-axis, and then this is our z. I'm going to draw this once, right? I'm going to draw two hybrid orbitals and allow them to overlap along the internuclear axis. And for just the sake of illustration, imagine your internuclear axis is your x-axis. So I've got one hybrid orbital here, and I've got another hybrid orbital here. And then, of course, there's the nub that we don't really draw in, but just for the sake of this illustration. Now, let's color this in. We have our sigma bond, right? Here, what we have are two hybrid orbitals overlapping along the internuclear axis to form a sigma bond. So here's your sigma bond. We have two hybrid orbitals that have overlapped along the internuclear axis. So imagining that internuclear axis to be the x-axis, you can take that forward when we draw our double bond out. Because when we make a pi bond, what's going to end up happening, and I'm going to put two of these on one graph. So here I have a y-axis. I'm going to leave the z out right for this, right? Because it's a little unnecessary at this point. When we draw a triple bond, I'll put it in. So I'm going to have two different atoms that are going to come together. Each one is going to form a pi bond from two unhybridized p orbitals. There's one p orbital on its y-axis. So we have another carbon atom. It's going to form a pi bond with the other carbon atom. We've got overlap perpendicular to the internuclear axis above and below the plane, right? So here we have two unhybridized p orbitals are going to overlap perpendicular to the internuclear axis and you'll end up with electron density above and below the plane, right? To form pi bond. It is not the same as two hybrid orbitals. These are not hybrid orbitals, by the way, right? So these are two unhybridized p orbitals, and they're going to overlap perpendicular to the internuclear axis to form a pi bond. One thing you might notice is check out how the hybrid orbitals in that example above are just laying flat across the x-axis, and they're just going to like overlap and form a molecular orbital. You get good orbital overlap. They're laying down on top of each other, right? These unhybridized p orbitals are going to find each other across space, above and below the internuclear axis. So you form a pi bond, but the overlap isn't as awesome. So, in other words, the bond is not as strong, right? So what you get is a pi bond. We'll draw our little y-axes here. We're all sort of grateful that we don't have to draw this every time. This is just for help in imagining what it might look like. The pi bond is where you have electron density above and below the internuclear axis. So here, I'll do this, I guess, in a different color, so we can sort of like differentiate this from the sigma bond. This is a pi bond. You're basically making like a little sandwich out of the x-axis. Now, in a double bond, you have a sigma bond and a pi bond. All double bonds. Write this down under here. Here we have a pi bond. All double bonds are made up of one sigma plus one pi. Here we're looking at a pi bond, right? With a double bond, you would have a sigma bond, like we see up above there, the two hybrid orbitals overlapping along the internuclear axis. You'd have that in between. And then the pi bond would be like an electron cloud, sort of like sandwiching it, like an Oreo kind of a thing, like a little one of those sandwich kind of cookies, right? That's a double bond. You have a sigma bond, which results from two hybrid orbitals overlapping, and then you have the pi bond, which looks, this pi bond looks like a double bond by itself, but it's actually just sort of like you're enveloping the sigma bond, which is made up of hybrid orbitals. And the way that you do it is using two unhybridized p orbitals. So I've got a situation here where we got our out of phase bits here and our in phase bits, and those are going to overlap, right? We're going to make a pi bond. So your pi bond, I'm going to draw a specific example. We'll draw ethylene. So CH2, and then there's a double bond, CH2. Right, with the Lewis structure for this, we've got two carbons that are doubly bonded together. Each one has a hydrogen. Two hydrogens, right? The bond angle is 120 degrees. So here you have theta is 120 degrees-ish, right? And you remember from Gen Chem, right? Because now each one of those carbons has 3 electron groups around it, right? I've got 2 single bonds and a double bond. That's 3 electron groups. We have a 120-degree bond angle. How do we hybridize this? How do we get that double bond from hybridizing these orbitals? So we're going to draw carbon. What do we have in this molecule? 2 carbons. 2 times carbon. I've got energy like this. Same old valence electrons. We have 2s. There's 2 electrons there. 2p. 2 electrons there. What do we have? 4 times hydrogen. There's 1 single electron in a 1s orbital. You're not hybridizing that. How are you going to do that, right? There's 1 electron, 1 orbital. It is what it is. So you got 4 of those. But we can take these. We can be like, listen, I need to make, in my double bond, that double bond right there, I'm going to have 1 sigma plus 1 pi, right? And then each one of these single bonds is a sigma bond. So if you're only looking at 1 single carbon, and they're equivalent, so you can just look at 1, right? Be like, all right, I see that each carbon has 3 sigma bonds and 1 pi. I have 2 single bonds. The carbon is bonded to 2 hydrogens. Those are the single bonds. The double bond is made up of 1 sigma and 1 pi. So I can use hybrid orbitals to make my single bonds. In other words, I can use hybrid orbitals to make my sigma bonds. But in order to make a pi bond, I need 1 unhybridized p orbital. So you're going to take an s orbital, 2 of your p orbitals. This will give you 3 sigma bonds, doesn't it? And I took an s and I took 2 of the p. So I have an sp2 hybrid orbitals. I have 3 of them, and I'm leaving 1 p orbital unhybridized. So I took, in other words, s and 2p, so 1, 2, 3, and then I left that by itself. I'm going to use that thing to make a pi bond. So I'm going to put 1, 2, 3, 4 electrons in. Here, I'm going to say this is going to be used, the pi bond, right? And these are going to be used for the sigma bonds, these sp2 hybrid orbitals. That's going to be used to make our 3 sigma bonds. So now we can draw this out. Thankfully, this is where Lewis is nice. You can draw the Lewis structure and you don't have to draw all these lobes. But if you want to know, like, all right, this is how we're going to use, or this is how we imagine we might use these electrons, it might not be bad to draw this out in terms of using our hybrid orbitals, or these big fat lobes, right? They look different, a little bit different. Our s orbital is a sphere. We see that with our hydrogen, right? But I'm going to take 1 of my sp2 hybrid orbitals, and I'm going to allow it to overlap with the other sp2 hybrid orbital on the other carbon. Remember, there are 2 carbons. Each one of them has this little setup going on. So, in other words, I got a 2 hybrid orbitals overlapping there to make a sigma bond. Each one of these carbons is going to have 3 of these hybrid orbitals, right? So I got 2 more to draw. And then the hydrogens come in, and that's just 1s, right? So we make those sigma bonds. I'll draw the H's in to make it easier to see what's going on. And I'll color in the sigma bonds. So these are all single bonds, carbon-hydrogen single bonds. The double bond is made up of a sigma plus a pi. Where are we going to get the pi bond? The unhybridized p orbital. So each one of those carbons is going to have an unhybridized p orbital. And remember, those look like this. So this is a p orbital, right? I'll just say this is out of phase. Each one of those is going to have one. When they overlap above and below the internuclear axis, you end up with a pi bond. So this, all this right here, and all this right here ends up being part of the double bond. So we've got sigma. Let me put this in a different color so you can see it. We have sigma, sigma, so two single bonds there to the hydrogens, another two over here, and then there's a sigma bond and a pi bond involved in the double bond. So all double bonds are going to be one sigma and one pi. We have that going on. I get that this looks like a triple bond. It is not. I'm going to draw an example of a triple bond in a second. You'll end up with another pi bond that's coming out of the plane and like sort of out of the page and into the page. It's really just these two unhybridized p orbitals. This electron density is going to overlap perpendicular to the internuclear axis. And we imagine that to be our x-axis there. So across, like horizontally, right? So our double bond will be a sigma and a pi. One thing you want to note, and this might not be a bad idea to go back to the sp3 hybrid orbital up here. Notice how I've got 4 hybrid orbitals. So all up here, I have 4 sp3 hybrid orbitals. They came from an s and 3p. So really, what do I have here? I have 25% S and 75% P character. In the hybrid orbitals. Right? I got 4 hybrid orbitals. One of them, comes from S character and the other 3 come from P character. So in other words, 25% and 75%. Turns out the more S character you have, the stronger the bond. Look down here. I have 3 hybrid orbitals, right? So we've got, I'm going to get rid of this, sort of just in our way here. I have 3 hybrid orbitals, 33% S character in the hybrid orbital, and 67% P character. This has a greater percentage of S character. So in other words, a double bond is stronger, has a greater bond energy, is more difficult to break, right? Or lets out more energy when it's formed than a single bond. So double bonds are stronger and shorter than single bonds. And then the other thing that we note here is that we've got theta. I won't put it on the diagram because we already drew that above, is about 120 degrees. The electron geometry, this is where we're going to be, this will be an important one when we talk about sp2 hybridized carbons. This is trigonal planar. This is flat. Put this in parentheses. When we do chemistry on sp2 hybridized carbons, don't be surprised when we end up with two different products. You can attack one of those carbons from the top or the bottom. It is flat like a pancake. The sp3 hybridized carbon, it's not flat, right? It's a tetrahedral shape. So it's got what we call shrubbery hanging out, in front of you, hanging out in back of the carbon, hanging out to the side, whatever. So you're going to end up with what we call a specific stereochemistry as a result in your product. With the attack of an sp2 hybridized carbon, you get what we call mixed stereochemistry, because you can attack from the top and you can attack from the bottom. It's flat like a little pancake. That'll be important when we start talking about substitution and elimination reactions. So in other words, up here, again, or S character, the stronger the bond. Here's the thing though. If you're looking at these hybrid orbitals overlapping along the internuclear axis, right, between those two carbons, so this thing right here, highlight that, this sigma bond is what I'm talking about in the middle there. You get a good orbital overlap, you get a nice strong bond, right? You have two unhybridized p orbitals overlapping perpendicular to the internuclear axis. The orbital overlap is not as awesome. So when you're talking about a double bond, you're not talking about two sigma bonds. You're talking about a sigma bond and a pi bond. The sigma bond is stronger than the pi bond. So when we break a double bond, or when we use electrons from the double bond to attack something else, it's probably from the pi bond. So this helps to just give us sort of like some kind of an image in our brain for like what's going on when we work through these mechanisms. And the last example that I want to share with you is going to be, at least for the purposes of this class, is where you have a central atom that only has two electron groups. Notice how with the sp2 hybridized carbon, we have 3 electron groups, right? We have 2 single bonds, each to a hydrogen, and then we have that double bond to the other carbon. So we have 3 electron groups. We do have a situation with carbon where we can have 2 electron groups. So lastly, for this class, we have a central atom with 2 electron groups. And for the purposes of this class, so in other words, for carbon, this can be one single and one triple bond. Remember, carbon only has 4 valence electrons. So in organic chemistry, it's nice. We look at carbon and it forms 4 covalent bonds, right? You can have a single and a triple, or 2 double. 2 double bonds or a single and a triple bond for carbon with its 4 valence electrons. In that situation, you have 2 electron groups and they're all involved in bonding. So for example, we can take acetylene, right, or ethine. We have a triple bond between the 2 carbons, and each of those carbons is singly bonded to a hydrogen. Let's go ahead and draw again, increasing energy, and we're again exaggerating our 2s, 2p. This will be for 2 carbons. Each carbon has this little setup going on. We have 2 hydrogens, right? And again, with its 1 valence electron in the 1s orbital, we're going to hybridize our atomic orbitals on the carbon. What do we see here? We see a triple bond. All triple bonds these are not 3 single bonds. They are not 3 sigma bonds. All triple bonds are 1 sigma plus 2 pi bonds. We know that in order to make a pi bond, we need unhybridized p orbitals. So what are we going to do? We're going to hold 2. Ignore that electron for a second. It's the orbitals you want to focus on. We're going to save these as unhybridized p orbitals for pi bonds, just like we did with the double bond. But now instead of the double bond where you only have a sigma and a pi, we now have a sigma and 2 pi. What does that leave us with? It leaves us with an s orbital and a p orbital to make sp hybrid orbitals. 2 of them, right? These can be used for sigma bonds. You can also use hybrid orbitals for lone pairs of electrons. With carbon, we're not going to have to worry about that. We've taken an s and we've taken a p atomic orbital, and we have created 2 sp hybrid orbitals. We have spared 2 of the unhybridized p orbitals. I'm going to put those here. These are our little unhybridized p orbitals. We just did not bother with those. Again, we still have 4 atomic orbitals, right, that we have mixed together, 2 of them to make 2 sp hybridized orbitals, and then 2 that are left alone. We're going to fill the electrons. And these right here are going to be used for our pi bonds. Right? So you can draw this out. Each carbon is going to have that set up. So what do we have? We have 2 hybrid orbitals. First hybrid orbital, I'm going to draw along the internuclear axis, overlapping with the other hybrid orbital on the other carbon. So that takes, each one of those carbons is going to use one of those hybrid orbitals, half filled, right, with an electron. So I'm going to make a sigma bond there. Each one of those carbons has a remaining sp hybrid orbital. I'm going to draw it along the internuclear axis, overlapping with the s orbital on the hydrogen. Nothing to hybridize there, right? Just 1 electron, 1 orbital. So there you have it. Each carbon, right, has 2 sigma bonds. And then check it out. So each one of these carbons has 2 unhybridized p orbitals. So we're going to take one of them, say along the y-axis here, just like we did with the double bond. We're going to allow these to overlap perpendicular to the internuclear axis. Just pardon my terrible drawing here. And we have created 1 pi bond. Right? So if this was a double bond, this would do it. But this is a triple bond. So we have another unhybridized p orbital along the z-axis, don't we? And so we're going to allow this, imagine anyways, this is going behind or into the page. And we have another one coming out of the page. It's still a pi bond. Draw this, color it in just a little bit darker so that you can see that there's two here. So with our triple bond, we have two pi bonds, and we have a sigma bond. So here we have a sigma, we have a sigma, and a sigma. Those are used from our hybrid orbitals. Here we have a pi, and we have another pi. That's our triple bond. So with our triple bond, we have 50% S and 50% P character. If you look at the hybrid, right, we have 50% S character, so we have an S orbital, and we have one of the P orbitals, so 50% there. So 50% is greater than 33%, which is greater than 25%, right? So the greater the S character, the stronger the bond. So a triple bond is shorter and stronger than a double bond, which is shorter and stronger than a single bond. If you're trying to sort of imagine this, instead of using bond energies or, memorizing numbers or memorizing anything really, just try to imagine that these unhybridized p orbitals are reaching across the internuclear axis, sort of reaching for each other to hold hands, I guess, right? And overlap, right? So the bond is not going to be very strong because the overlap is not as awesome as it would be if you had a hybrid orbital just laying on top of the other hybrid orbital, right? So that sigma bond is pretty strong. Those pi bonds are not very strong. They have to really reach for each other. So we shorten the bond. We get another one in the triple bond, so it's even shorter, right? And all of this is sort of just experimentally determined. This is just me talking about, hey, imagine, like, instead of memorizing bond energies, like that triple bond is shorter than the double bond, which is shorter than a single bond. Just sort of just imagine this picture in your head of these unhybridized p orbitals sort of overlapping perpendicular to the internuclear axis so that they can form a molecular orbital. So it's a little shorter and it's a little higher in energy. What else is going on here? We've got a linear molecular geometry. So theta is 180 degrees. What else is going on here? Again, all triple bonds are going to be that 1 sigma plus 2 pi bonds. It's not simply just 3 single bonds. All single bonds are sigma bonds. I don't have 3 sigma bonds here. I have 1 sigma bond between the 2 carbons, and I have 2 pi. Each carbon has 3 sigma bond, or I'm sorry, each carbon has 2 sigma bonds. I see 3 total, right? But for each carbon, I have 2 sigma bonds, but the triple bond itself is 1 sigma and 2 pi. So, and with the Lewis models, we're not drawing these lobes, right? So I can take that molecule and I can draw it like this. There's the single bond, there's the carbon, there's the triple bond, there's the other carbon, there's the single bond, right? So it's a lot easier to draw like that. But using valence bond theory, it helps us to just sort of like imagine, what are we doing with these valence electrons? How could these be overlapping, right, to form these molecular orbitals? So let's do just kind of a little recap for those who enjoy memorizing things. You shouldn't have to, but if that's how you prefer to do things, we're going to take our bond length, remember from Gen Chem, is directly proportionate to your bond strength. The shorter the bond, the stronger the bond. So in other words, the energy will be higher. We care about that. More energy is given off when the bond is formed. More energy is required to break it. So we do care about that when we're doing synthesis, right? All single bonds are sigma bonds. And we can use hybrid orbitals to make those. All double bonds are going to be 1 sigma and 1 pi bond. All triple bonds are going to be 1 sigma, again from a hybrid orbital, right? And 2 pi bonds. In this class anyways, for carbon, we will occasionally talk about the hybridization of a nitrogen because we'll be discussing the availability of a lone pair of electrons on a nitrogen. At some point, when we get there, we'll be like, hey, remember hybridization? And we'll give this some more thought. But for carbon, if you have 4 electron groups, this can be bonding or non-bonding. Non-bonding would be like lone pairs, right? Carbon typically forms bonds with all of its valence electrons, but carbanions do exist. We can have a lone pair of electrons on a carbon. We'll discuss those further as we move through the semester. But if we've got 4 electron groups, you can bank on sp3 hybridization. You can bank on theta being approximately equal to 109.5 degrees. You can bank on 25% S character and 75% P character. And you will have a tetrahedral electron geometry. If you have a situation where your central carbon has 3 electron groups, we have an sp2. If this is hard to remember, look at what you have there for atomic orbitals. 4 electron groups, you have an s, and you have 3 p orbitals. There are 4 atomic orbitals that came together to make that particular hybrid. With 3 electron groups, we have an s atomic orbital and 2 of the p atomic orbitals, right? So 3 atomic orbitals came together, 3 electron groups. We have an sp2 hybrid. Theta is somewhere in the ballpark of 120 degrees. We're going to have 33% S and 67% P. These little numbers you don't have to remember, but just in terms of remembering, hey, what's stronger? The more S character you have, the stronger the bond. This is going to be trigonal planar. Planar means flat, right? And then for 2 electron groups, we're going to have an sp, hybridized carbon, theta will be 180 degrees. We're going to have 50% S, 50% P, and you'll have a linear molecular geometry, or an electron geometry that is linear. Okay. So that ought to do it for hybridization. In the next video, we're going to be talking about intermolecular forces and the physical properties that are affected by the intermolecular forces. And that ought to take care of the first bit of our general chemistry review. From there, we'll move into acid-base chemistry, and that'll be it for our general chemistry review. And we'll jump into the orgo after that.